Arden Labs, specializing in high-performance software consulting, training, staffing, and development. Module 10 Channels. You are now watching Lesson 10.7, Fan-Out Bounded.
One of my favorite channel or signaling patterns is the fan-out bounded pattern. This is a situation where you have a discrete amount of work, let's say 2,000 pieces of work, but you don't want to throw 2,000 go routines at the problem. You really want to control the number of go routines that are going to work on this. And so what we're going to do is bind or bound the number of go routines that actually get any work done. We're not going to create 2,000 and then limit only 8 like we saw with the fan-out semaphore pattern. We're really going to end up kind of in this pooling idea, but it's not an unlimited pool. We know exactly how much work needs to get done. We're just going to limit the number of go routines to do it. So on line 186, there we are where I'm defining 2,000 pieces of work to do. You may not have ever seen the syntax before with an array or a slice, but you can see that I'm setting an index position for that last piece of work that will create a slice with a length of 2,000. Now, again, I'm going to use my runtime numCPU as my initial magic number for this pool. So there it is. We're going to define, in my case, 8 go routines that are going to do the full work of the 2,000 pieces of work that we have here. I'm going to use a wait group to orchestrate when all this work gets done. So there it is. We've got our wait group. I add 8 to the number of go routines, and then I make a channel on line 192. Now this is a buffered channel. And again, the idea is that we're going to be feeding these 8 go routines the 2,000 pieces of work. And we could really limit our memory here. We don't have to create a buffer channel of 2,000. I mean, 2,000 might be small, but what if there's 1,000,000 pieces of work that we need to get done? I'm not going to create a buffered channel of 1,000,000. So what's nice here is that as long as we continue to keep some data flow in the channel, it doesn't have to be a very large channel to feed off of. And I like, again, matching that with the number of go routines we're going to have in the pool. You're going to see, if you did some benchmarking, that using a buffer 8 or 2,000, you're going to get the same results. All right, so we've got a buffer that we're going to feed work into for our bounded fan out here. We're going to go ahead and launch those 8 go routines on line 194. So there they are. We're in our loop. We launch those go routines, and those go routines are blocked on line 197, waiting for work to do. Which go routine is going to do what work? Again, I don't know, and I don't care. This is concurrency. It's out of order execution, and it shouldn't matter. But on line 196, you're seeing for the first time here the use of the keyword defer. Defer is just that. What it's saying is execute this statement, but not now. Defer it, in this case, for when that function or go routine terminates in this case. So we're going to decrement that wait group once there's no more work. And that will happen when the for range terminates, and the for range will terminate again once we close it. So there we are. We're going to have a pool, right? We're going to fan out 8 go routines. They're going to be waiting for work. Eventually, we're going to tell them there is no more work. They're all going to terminate. They're going to decrement that wait group, and then we're going to be able to move on. So how does all of that work? Let's come in here on line 204. So on 204, now what we're doing is we're ranging over that collection of work. Remember on line 186, we had that work right there, and now what we're doing is ranging one value at a time, and we're signaling or sending that work on line 205 into that channel. That's going to start getting those go routines busy doing work right there on line 197 and 198. Once we've got 8 go routines busy, yep, we're going to be blocking here for sure, but eventually that go routine finishes, comes back into the range, and we'll just keep that data flowing. There'll be very small latencies there. We're not going to feel it for the amount of work, and we're able to keep that memory profile very, very low as well. But notice what we're doing here. On line 207, once the last piece of work is submitted into the buffer channel, we close the channel immediately. That's beautiful because we're going to stage the signaling without data, right? We're going to stage that cancellation and shutdown. So the go routines get to continue to flush the buffer out. Eventually, there's no more data. The close signal starts to fire. these go routines start to terminate. They start to decrement those weight groups. And once we finish the close, we're now at our guarantee point on line 208. We're blocked, waiting for all of those 8 go routines to decrement that weight group back down to 0, which eventually they do, and we move on. So I love this fan out bounded pattern because what it does is it lets me stage a tremendous amount of work that where we may not feel comfortable throwing a go routine at every task. And it also allows us to minimize the memory resources that we need. You're still going to have to kind of figure out what is the magic number for this kind of fan out pool that we've created. But normally that num-CPU is an amazing starting point, and usually it does give you the results that you need. So we're going to see a fan out bounded pattern come back up before we're done, because at some point we're going to get into profiling and tooling, and we're going to do a little bit more multi-threaded programming. So the fan out bounded pattern, one of my favorite.